a phenomenon observed by the Parker Solar Probe mission. But if you're not a solar wind person, you can also view this as an application of some classical ideas about shear-driven turbulence. In this case, probably more magneto-hydrodynamic shear-driven turbulence, but really it's shear-driven turbulence in a collisionless plasma. So,
and much of what I'm saying is contained in a paper by Ruffalo et al., Astrophysical Journal, 2020, and I'll show the reference here, but I'll probably show it a couple of more times later in the talk. So let's get started then. This is a picture of a solar eclipse, and it's a beautiful picture. But one thing that, and you've seen these before, I'm sure, one thing that really stands out in these kind of pictures is the structure that you see in the corona when the disk of the sun is blocked by either the moon or by an occulting disk. In this case, it's the moon, and you see that the pattern that you see, which is actually scattering from the plasma, is usually interpreted as magnetic field. And if that's to the extent that that's true, and I'm pretty certain that it is, what this is telling you is that the magnetic field is dominating what you're seeing. The magnetic field is controlling the plasma when you're at these altitudes from the sun. Of course, inside the sun, in the photosphere, convection zone, the convection and plasma motions are more dominant. But once you get into the corona, for quite a few solar radii moving away from the sun, the magnetic field is dominating over the motion of the plasma. And we can call this this almost appearance of hair as striation, elongated structures, strong gradients across what appears to be the magnetic field, and weaker gradients in the direction along the magnetic field. Now, a question that you might ask is, does this control by the magnetic field extend infinitely far out? Probably not, because the magnetic field eventually has to fall off with distance. Eventually, like 1 over r or 1 over r squared, depending on what model you use. But the dominance of the magnetic field can't last forever. But where does it end? And we're going to be looking into that in this talk. Here's a couple of more pictures that I put in. This is a similar picture, but a bit maybe less detailed than the last one. This is a photograph. And here's a white light LASCO movie from 2002. And here you can actually see the motions of the plasma. And except for occasional large blobs of plasma that are ejected, you can see that the flow is apparently dominated by this radial flow, which appears to be guided by the magnetic field. So in more modern coronagraph studies, for example, this one from DeForest et al. In 2018, obviously false color, but they did a special campaign with the stereo core 2 coronagraph, and they did 36 seconds exposures that were highly processed. Now, I don't have the movie version of this, but if you saw the movie here, first of all, you can see several things. First of all, you can see the striations or spokes that are largely radial in direction. But the green is telling us something about density inhomogeneities. And in the dynamic version of this picture, you can see these blobs of green moving outward, not only moving outward, but in different radial spokes, even nearby different radial spokes. The blobs are moving with different speeds. In fact, the speed differences are up to 200 kilometers per second. Now, it's believed that in this region of the corona, the strength of the magnetic field is large, and measured in Alfven speed units, the magnetic field is probably between 500 kilometers per second and maybe even 1,000 kilometers per second, which is consistent with our ideas that I mentioned before, that the magnetic field is stronger than the plasma motions in let me call it the middle or outer corona. Yet another set of images, this one also from stereo, in this case using the stereoheliospheric imager, which is a variation on a coronagraph with extreme sensitivity, such that you can actually observe the solar wind moving at 30 or 40 solar radii in this picture, maybe even up to 50 solar radii. Of course, this is you're seeing scattering, Thomson scattering in the direction perpendicular to the image. So there is some integration over that direction, but even still, it's plain that closer to the sun, you see this striations with strong gradients across the apparent magnetic field direction. And then as you move outwards, you can see that the pattern, the dynamical pattern, seems to lose the striation and become more isotropic. And actually in this paper, I worked with Craig, and we computed structure functions in this region, keeping away from this coronal mass ejection, by the way. That's a discrete event. But in these regions where you have the smooth outflow starting to become more isotropic, we interpreted this in that paper as a transition from striation nearer to the sun to flocculation further from the sun. Flocculation refers to the character of sheep's wool, which is kind of more fuzzy and more isotropic. But this looks a lot like a transition from relatively anisotropic flow to more isotropic flow. So we're going to examine that here. And I like to advertise a future mission. This is from stereo, but if you like this kind of diagnostic and think that you can get a lot of good science out of this, then you will really like the PUNCH mission, which is in development. The PUNCH mission works on a similar principle, but it uses polarized light, so it gets information in the in-plane, out-of-plane direction. And also it has about 10 times or more higher resolution in each dimension. So there'll be a lot more information in PUNCH than in this picture.
So Bill, can I ask a small question?
Of course.
Yeah, so here, these are spectroscopy. I mean, how do you get so much of information from a spacecraft? These are how does one get it?
Well, what you're seeing is scattering from electrons, Thomson scattering. And they have extremely sensitive coronagraph-like imagers. And even still, the raw images that you get from this instrument on stereo don't look like this. Craig DeForest is absolutely brilliant at image processing, and he removes the star background, and he has they actually do K omega decompositions of the image and remove the parts that they don't want so that they can see the parts that are moving. I mean, in the middle of this picture, the electron density is only something like a few, probably 50 electrons per cc, but yet you're actually seeing that gas. It's kind of a really remarkable instrument if you think about it. You can look at this paper and the references in it. I can send the paper to you if you're interested. I don't build or analyze these data myself. I acted as the turbulence guy, helping Forrest on this paper. But I think that these are fantastic instruments where you can actually see rarefied plasma.
Excellent, yeah, indeed.
Yeah, it's really, and PUNCH is going to be like orders of magnitude better. Excellent. I mean, the finest scale, the pixel scale in this image, I think, if I remember correctly, is a few gigameters, which is around maybe slightly larger than the estimated correlation scale of the turbulence. So you're actually seeing very large structures, larger than the nominal correlation length. But PUNCH, by going more than a decade smaller scale, PUNCH is actually going to get into the inertial range, which is just amazing that we might be able to detect, say, an anisotropic Kolmogorov-like spectrum from several astronomical units distance.
And this spacecraft will be near the sun, near the Earth, or where is it located? It will be fixed?
Well, it's stereo. Stereo is in orbits that are removed from the Earth now. It's traveling along the same orbital path as the Earth.
Okay.
but not at the same position as
Okay.
the Earth.
Okay. Great.
So they're pretty far from the Earth, but they're an astronomical unit or so away from the sun.
Excellent. Okay.
So the reason, so that you have a stereoscopic image of
I see.
structures coming off the sun.
Great. That's a great idea. So they're basically 180 degrees, and they're looking at the sun from two eyes.
Yeah, that's right. So you get some three-dimensionality from that.
Indeed. Okay. Okay.
That's
Great.
right.
Okay.
No, it's really an amazing mission.
Okay. Very good. Yes. Thank you.
So anyway, here's a still picture taken from the same instrument. But what we've done here is we've taken one of Arkady Usmanov's three-dimensional global heliospheric simulations, in this case with a pretty simple boundary condition. And just simply, we've drawn the sonic critical point and the first and the Alfven critical surface here in yellow for this particular run, and then two different first plasma beta surfaces, the first plasma beta surface for the proton beta and for the total proton plus electron. For those who aren't plasma types, the beta is the ratio of the mechanical pressure to the magnetic pressure. So when beta is less than 1, that means the magnetic field is the boss, and the plasma has a hard time moving around the magnetic field, and that's true under these surfaces where the beta is much less than 1. But then at some point, when you move beyond these surfaces, the mechanical pressure and its differences become large enough to move the magnetic field around. And that was our claim in the Forest et al. Paper, that this transition from striation to flocculation was occurring because the plasma pressure and also the differences in the velocity field became large enough to actually move the magnetic field around. So the condition for beta equals 1 is some constant times the pressure is approximately equal to the magnetic pressure here. And this is discussed in Chibber et al. AppJ Letters 2018. So what else happens because of this transition? Well, we developed this idea about what Parker Solar Probe is seeing based on sort of this cartoon. Now, I've already prepared you some for this, that below the Alfven critical surface, where the Alfven speed equals the plasma speed, the magnetic field is stronger than the flow, and it's considerably stronger than the mechanical pressure, because you don't get to plasma beta equals 1 until outside the Alfven critical surface, typically. So this region, this is not a strict surface, it's really more of a region, but let's think of it as a surface. Below that surface, the magnetic field controls everything, and you see this hair-like striated structure. But as soon as when you pass this surface, now the flow speed or differences in the flow speed might be large enough to start something like, say, a Kelvin-Helmholtz instability, and eventually the flow speed is large. The flow speed, the mechanical pressure is low compared to the tension in the magnetic field lines, and out here someplace you expect, say, something like a Kelvin-Helmholtz or a shear layer instability. I don't really view this as a linear instability, because after all, inside these tubes, the flow is not necessarily laminar. It's just confined. Think of it as a pipe, possibly with a net flow towards the right. But there's a lot of fluctuations in there already, and they're not necessarily infinitesimal. But as soon as the pipe becomes weakened, then those perturbations can cause nonlinear instabilities, and in principle, rolling up the magnetic field. And those reversals of the magnetic field are what people have called switchbacks. So in this Ruffalo et al. Paper, we've made the argument that the flocculation and the transition from striation to flocculation and the transition from this radial flow and radiomagnetic field to this flocculated appearance of the plasma, that these things are caused by the same process, which is some kind of shear layer instability in this region outside. Anyway, that's the basic picture. So let me just remind you, and probably there's a lot of fluid mechanics people on board here today. But let me remind you of what a hydrodynamic mixing layer looks like. This is from a simulation by Attili and Bissetti that I got off the internet. You have flows, fast flow on the top, slower flow on the bottom, separated by a thin plate. This is a tracer or a tracer of fluid elements in the vortex layer. When the plate ends, the two fluids can start to mix. There's an instability region, which is actually pretty brief, and then you get finite amplitude roll-ups, and eventually a transition to something more like homogeneous and isotropic turbulence downstream. So what we think the switchbacks, as well as the transition to flocculation, are caused by is this kind of Kelvin-Helmholtz-like roll-up, except of course it's in a magnetized plasma. So the transition is initiation, roll-ups, fully developed, and then isotropic. And I see that Yan Yang is online, so therefore I'm going to show you Yan Yang's recent movie that she made of MHD Kelvin-Helmholtz, actually for another project, but the parameters are not so different from what we expect in this flocculation region. In this case, the perturbation is very small. You're looking at the vorticity, and as time goes on, you start to see finite amplitude fluctuations, and eventually roll-ups. Now here there's a horizontal magnetic field, and the reason that you can get this instability again is that that the velocity differences in the initial conditions exceed Chandrasekhar's condition for suppression of the instability, which is that the velocity difference, if the velocity difference is less than the Alfven speed of the horizontal magnetic field, then you can't get this kind of instability. In this case, you exceed that threshold and you have a perturbation, so it grows into these nice Kelvin-Helmholtz-like roll-ups. So you can imagine what you would see if you had a lot of these, and also you can imagine what you would see if you were a spacecraft passing through them. So let's move on and just look at the history of this a little bit. The history of our interest in this goes back to working with Mel Goldstein in the late 80s, when we were interested in Kelvin-Helmholtz roll-ups on the flanks of the magnetosphere. And we ran our codes, which were not very high resolution back then. And we ran hydrodynamic Kelvin-Helmholtz instabilities, like the one up here. And there you see like full roll-ups pretty easily if you put in a perturbation. For MHD with a moderate shear and a finite magnetic field, in this case you didn't get complete roll-ups because the magnetic field stabilized the roll-ups. You still get large deflections of the magnetic field, but you don't get the complete roll-ups. There are some other simulations that we did back then that did have roll-ups. In '96, Bob Rosner and Malagoli et al. Published a nice paper showing how the magnetic field, these are magnetic field lines now, in a case where you do exceed this minimal shear intensity velocity jump, large velocity jumps that can actually produce complete roll-ups and reversals of the magnetic field. So when the shear is strong enough, you can get isotropization and switchbacks, in the sense that the initial unidirectional magnetic field actually on occasion bends back in the 180-degree reversal. These are just a lot of references. Again, the Chandrasekhar reference. There's a famous paper by Lau and Liu and Miura and Pritchett in the early 80s. There are nonlinear studies in the beginning in the early 80s and even up to in plasmas fairly recently. People have studied this kind of thing in coronal streamers. Russell Dahlberg, Giorgio Einaudi, Franco Rapazzo. Mel Goldstein and his collaborators did a lot of this. I was one of those collaborators a long time ago. I still am. And in solar wind, people have seen polarity reversals in the 2000s. Landy et al., recently Squire et al. People have seen reversals in stimulations and in solar wind observations. But the big news from Parker Solar Probe is, and this was the first picture, more or less the first picture that I ever saw from Parker Solar Probe a couple of years ago at the AGU meeting, this top one. This is the first encounter. And if this is back, I guess, early December 2008. I guess I'm losing which
November
year
18, yeah.
2018, okay. Oh, yeah, that's right. It's right on the bottom. 11/6/2018. Sorry about that. So here, this is really striking. You look at the radial component of the magnetic field in black here, and zero line is in the middle. And you can see that these huge spikes, many reversals of the magnetic field direction, even while the magnetic field magnitude in green is fairly constant. And the other two components of the magnetic field are fluctuating about zero, but you have these strong reversals of the magnetic field, and they get really large when the distance to the sun here at perihelion occurs, when you're close to the sun. This first pass of Parker Solar Probe went down to 35 solar radii, which was much closer than any human-made device had ever been up until that time. Now, if you blow up 1 hour of that period right here in the middle, you get something that looks like this at the bottom. And you can see again that there's a fairly constant magnetic field in green, and you see in black the radial magnetic field occasionally almost reversing, and in fact reversing here and over here on the right. So what's causing these reversals? Now, initially, people didn't automatically connect these reversals to the flocculation that I was describing. I mean, but when we saw it, because we had done that study, we thought that this was a pretty clear connection that should be examined more. So it turned out that we had also been studying this kind of phenomenon using these global simulations in advance of the Parker mission being launched. By Rohit Chibber did a lot of this work with Arkady Usmanov, Mel Goldstein, and myself. And even if you use a simplest boundary condition, an untilted dipole magnetic field, and reasonable boundary conditions on the inner part of the code, this is a three-dimensional MHD code now, but it's a three-dimensional MHD code that also tracks the, it's a Reynolds averaged model. So we have a subgrid or unresolved turbulence amplitude that we call Z squared. So these are the resolved fields that you see here, the density. And then we also follow a turbulence amplitude and a correlation length. And if you look at how that Z squared, that turbulence amplitude, varies in this simulation, starting from an input near the inner boundary, you see that the turbulence amplitude grows and it becomes a maximum pretty near the Alfven critical point, which is exactly where we would like to trigger these instabilities that I was showing you in our cartoon. So you actually get quite a bit larger turbulence amplitude than you had initially. And this, you might guess, if this turbulence can start to isotropize, that of course it's large enough to generate these switchbacks. Now, the other curves on here, there had been some remote sensing data, radio scintillation studies done by Lotova. That's a kind of remote sensing where you look at radio sources, astronomical radio sources, and you look at them in grazing incidence to the sun. And if you look at them along lines of sight that are close enough, you can deduce what the turbulence amplitude is. And you can see that there's a subtle but very interesting feature that actually Lotova made quite a big deal about, saying that there was enhanced turbulence near this region, which happens to be pretty close to where we see this peak of turbulence. In the same simulation that we did, the actual solar wind velocity is accelerating through this region. So we might expect very well that just outside this Alfven critical zone, that we get some special kinds of turbulent behavior. So here we've taken the hour average Parker solar field data from the first encounter, and that's in the dark blue curves. The top three are the three components of the magnetic field during that encounter, measured by Parker, and the bottom three are the radial, azimuthal, and latitudinal flow components, also from Parker in dark blue. The red is the resolved component of our three-dimensional Reynolds averaged MHD simulation. And you see, it doesn't really follow the Parker data all that well. I mean, it very coarsely, the radial magnetic field does follow the trend of the Parker data, but it doesn't follow it in detail. There's a lot more fluctuations in the Parker data. But if you take our z-squared, our turbulence amplitude, from our Reynolds averaged accounting of the turbulence, and if you take the square root of the variance and say, well, the amount of turbulence that we should have, it should be something like what we observe in the resolved component, plus or minus the standard deviation that you get from the Reynolds average turbulence, then you get this background of this purple envelope that we draw here. Now, it doesn't do all that well for the velocity field because we don't have enough resolution on the inner boundary. But for the magnetic field, that purple envelope pretty well accounts for the large fluctuations that we see in the Parker data. Now, of course, that's a statistical argument, and you can't use the purple envelope to argue that you should actually necessarily switch back. You need to do more than that. But let's look in a little more detail at the Parker data. How am I doing for time? Do I have another 20 minutes or so, maybe?
Yep.
Yeah, okay. So, so here's the radial speed from Parker encounter 1, measured in Alfven speed units, both in the 1 hour data in dark color and the kind of reddish or orange color. That's the 0.8 second, 87 second cadence radial speed. Oh no, I'm sorry. That's the radial speed normalized to the either smoother or less smooth Alfven speed. And you see that there's these spikes. And if you actually measure the velocity increments, the 10-minute increment of the radial speed in units of the Alfven speed, you get this curve here. And the darker sort of orange color, you can see that this many times exceeds 1. Now remember, Chandrasekhar's criterion for suppressing the instability is when the velocity increment is less than the Alfven speed. So a lot of the times here, the magnetic field is still strong enough that the velocity differences, the velocity increments, cannot turn the magnetic field around. But we can also see that in many, many cases it can. So the fact that this velocity increment exceeds the Alfven speed means that you very well could have strong Kelvin-Helmholtz-like instabilities, even though the magnetic field is there and pretty strong, but it's not strong enough to stop the roll-ups in these cases where this exceeds 1. So we thought that was pretty interesting suggestion. But then we also looked at the distributions of the tangential velocity, because if you're starting to roll up the plasma speed, then you should see features in the transverse velocities. So on orbit 1, you can see the tangential velocity here had a broad distribution in several peaks. And that's kind of often characteristic that you see several average speeds blurred together. And this is what you might expect if you were seeing different streams in different stages of their instability. When you get very close to perihelion here, in an 8-hour period around perihelion, you see that the tangential velocity is strongly skewed towards the positive tangential direction. And then on the way out again, it's more or less balanced. Now, the fact that you have this skewed velocity distribution is very likely due to the fact that some of the magnetic flux tubes have remained strong enough that they can still co-rotate with the sun. In other words, they're still some of them are still on the left side of that instability boundary that I drew in the cartoon. Now, why it should exceed the co-rotation is another story, and we're actually not sure that that measurement is accurate. The people on the Parker Solar Probe mission are still examining that, but if you're exceeding co-rotation, then there's something else there that needs to be explained, and we don't necessarily have an explanation for that. It might not even be real, because there's viewing problems on the spacecraft, namely the fact that they need a giant shield to prevent everything from being vaporized by the sun. But a lot of these data are probably pretty accurate, but when it gets really close to the sun at early orbits, we're not sure. You can also look at the distributions of the magnitude of the magnetic field. And once again, on the way into the first encounter, at perihelion, and on the way out. Again, on the way in, you see that this is compartmentalization. It's almost as if you've encountered several different magnetic flux tubes, and they have different strengths. Similarly, you're seeing that at perihelion. You don't have the same problem with the magnetic field instrument that you have with the velocity field instrument. So this is probably very accurate here. And then on the way out, things seem to be pretty quiet, and you have a pretty tightly distributed magnetic field. But in any case, the presence of these spikes, in all cases, means that the magnetic field is compartmentalized into regions that have pretty well-defined values of the magnetic field strength. In other words, the magnetic field looks like it might be locally constant. So in order to examine some of this, Yan Yang, who I think is still with us. Yes, I think she is. Yan did a very nice set of simulations for us. Again, Kelvin Helmholtz. She did them in 3 dimensions. The parameters are in the upper right here. It's not the world's largest resolution code. It's only 256 cubed, but I think it serves its purpose here. We have velocity jumps across 2 shear layers that are 3 times the average Alfven speed. The plasma beta is 1. The acoustic Mach number is 3.6. And then we have reversals of the flow and changes in the magnetic field strength in the same regions that the velocity changes. We can look at these at different stages of evolution and see if any features that we see resemble the Parker data. Now, this is quite a challenge to these codes, because this is a periodic code. This is not a 3-dimensional MHD simulation of the heliosphere. This is a cubic box of MHD compressible turbulence. And if the physics of this simulation, which is clearly going to be shear dominated, if it has any resemblance to the Parker data at all, it might be further evidence that the ideas that we're expressing could be relevant. So let's look here at a couple of movies. We have the X component of the magnetic field here in color, and we have the magnetic field vectors on the same plot. Over here we have the vorticity in colors, and we have the velocity field in arrows. So I'm going to start both movies, and you'll see that it develops pretty quickly. So you have this vorticity deformations here, and on the left-hand plot, when it turns green or blue, the magnetic field is switched back. So you can see that you are getting roll-ups, and I'm going to start the movie again when it gets to the beginning. But so you do get roll-ups intermittently, and you also get these like interesting shock or rarefaction shock-like structures at places where the velocity field bends around a corner. Those haven't been observed, but we're asking the observers to examine that possibility. Let me start this over again to just show you the instability region again. So the initial stages, you start to get the roll-ups, and you get these reversal regions sporadically. So we get some reversals. Things are pretty complicated. We can look at some distributions and correlations and things like that, and see how they compare to the Parker data. So here we go. Here Again, the Minping Wan and Yan Yang simulations are on the left. We have some cuts through the simulation box, and you see that the black curve, the B radial, actually is here. It's negative, and there's a switchback, and then it goes back to the original polarity, and then it switches back again. And in between, in the yellow or gold color, you see that the magnitude of the magnetic field is kind of constant in patches, changing from one patch to another, sort of near the place where the switchback occurs. Not exactly at the same region, at the same place, but nearby. And David Ruffalo in Thailand is exploring with his students the statistics of this constant magnetic field regions. And he's going to have a paper on that pretty soon, I think. On the right, we have the Parker data. And in the green on the top, you have the magnetic field magnitude. And again, you have this patchy magnetic field magnitude regions. The black, which is the radiomagnetic field, again, sporadically undergoes large deflections and sometimes actually has reversals. Now, remember that the higher the time resolution of the data, the more likely you are to see stronger deflections of the field. So if you go to our average data, this is an hour here. But if you go to higher and higher resolution data, you see more switchbacks. But if you take these data sets and you look at the distributions of the radial field and ask the question on the left here, how often do you get switchbacks? Well, here's from the simulation. Here's the dominant polarities, and again, it's compartmentalized. You have radial fields, a lot of radial fields with this value, and a lot of radial fields with this value, and a much smaller fraction of the time you see the radial field reversing sign. Now, if you take this hour of Parker Solar Probe data and do the probability distribution of the radial field here, you get this curve. And you can see that the shapes are very similar. There's preferred values of the magnetic field radial component in both cases, and a tail with a non-zero probability of getting actual reversals. So that is it's kind of similar distributions, let's say. You could do the same thing for the magnitude of the transverse velocities normalized to the Alfven speed for the Parker and the simulation. In this case, you can plot them on the same plot because they're normalized the same way. And the darker color is the Parker, and you see that the transverse velocities are pretty well limited by the Alfven speed. And the same thing is true in the MHD simulation, that almost all of the deflections of the transverse velocity are at values less than the Alfven speed. And why is that? Well, if you go back to the Rosner paper from 1996, they made this argument. They said that when you have a shear instability that deflects the magnetic field, that there's a local dynamo action. It actually amplifies the magnetic field. But when the transverse velocities reach their maximum, they cannot you cannot get transverse velocity larger than the amplified value of the magnetic field. And then they made the point that that's not really dynamo action, because that's going to relax pretty quickly when you get out of the shear instability region. But you sort of expect this limitation to be present. If you look at the PDFs of the magnetic field magnitude, that's also interesting. Simulation on the left, and again you see this compartmentalization. You have signatures of discrete flux tubes with different values of the magnetic field strength at two different times here. It's a persistent feature. And the Parker data, again, you have the PDFs of the magnetic field taking on certain discrete values. So I would argue that these are similar distributions for all of these quantities. So we think that this is a indication, looking at these statistics and the similarities, at least qualitative similarities in the statistics, we think that there's that this is supporting our idea that the nonlinear Kelvin-Helmholtz roll-ups in the presence of a significant magnetic field can occur outside the Alfven critical zone, probably near the first beta equals 1 surfaces, and that these phenomena, our hypothesis is, may simultaneously explain the magnetic field switchbacks in Parker Solar Probe, and also the observed striation flocculation transition. Now, there's more to do to tie these together, but I think our hypothesis has passed the first test anyway. And we found in this analysis consistency in this picture with the frequency of reversals, the patchiness of magnetic field magnitude, the distributions of tangential velocity, the sharpness of the velocity changes. I didn't show it, but it's also, there's a similarity in the nature of the alphenicity. And also, I didn't show data on it, but there's also evidence in both cases of compressional or density rarifications near the edges. And that in particular, I think, is going to require additional study to lock that up. It's an intriguing possibility because, as I said, we've seen just heuristically, looking at the data plots, what looks like some evidence that there's density changes and alphenicity changes at the edges of these patches. But I don't think that anyone has quantitatively established that yet, although I think there's several groups working on those two aspects of the switchbacks. There's further impacts that can be explored that I'm not going to go into in this talk. One of them is that if this energy source that's in these differential flows in the flux tubes becomes unleashed in this region and participates in this roll-up, then in effect, that storehouse of energy is injecting more kinetic energy and magnetic field energy into the very large scales of solar wind turbulence. So there's actually an extra injection. And what this would mean is it's contrary to the standard picture of solar wind turbulence, which is that it's injected at the inner boundary, low in the corona, in the photosphere, caused by stirring of the magnetic field lines and launching Alfven waves upwards. In this case, the energy is stored in the flows, and it's added to the pre-existing energy that people envision in the standard viewpoint. Another interesting thing, and Riddhi Bandyopadhyay is on this call, is that Riddhi, working at Princeton, did a very nice study using the ESIS energetic particle data on Parker Solar Probe. And he looked at the switchbacks in the magnetic field and also looked at the anisotropies in the energetic particles and found that it's very rare that the energetic particle anisotropies reverse when the magnetic field reverses. Now, this is in contrast to the Alfven wave propagation at higher frequencies. The Alfven wave propagation does reverse. If you're a plasma physicist, you know that electron distributions often have a feature called straw, which is a kind of beaming of the electrons along the magnetic field direction. And in fact, Parker Solar Probe data has shown that the electrons actually do switch back when they encounter a magnetic field switchback. But the 50, 100, 200 keV ions do not switch back as measured by ESIS, or that rarely switch back. And Riddhi has, in his astronomy and astrophysics paper that's in press, uses that fact to estimate what the radius of curvature is of the magnetic field at the switchbacks. And I believe that his statement is that it cannot be much larger than 4,000 kilometers, because if it were, then presumably the 100 keV ions would switch back, because particles tend to follow magnetic field lines unless the field lines are too bent, they bend too quickly, and the particles cannot do so because of their gyro radius. So that's another interesting aspect of this. And finally, just to give a nod to the other explanations for switchbacks, our picture does not preclude having other perturbations that arrive in this region from lower altitudes. There's evidence for other types of perturbations. For example, type 2 spicules observed by DePontiu and Samanta et al., may actually be the origin of these differential flows. But in any case, those are perturbations that are going to participate in this turbulence that we envision. There also can be remnants of interchange reconnection, which is probably the prevailing view as to what the switchbacks are. But there are people like Anna Tenerani at Texas at Austin and others who have done simulations showing that when you kink the magnetic field due to reconnection much lower in the corona, that those kinks actually fade away by the time you get to 30 solar radii. So there might be some remnants of interchange reconnection, but and if there are, they could act as catalysts to trigger the instability that we're talking about. But we think that our mechanism is more likely the immediate reason why you get the switchback field. And finally, there are various waves from the photosphere, from the chromospheric furnace and so forth, which are mostly at higher frequency and smaller amplitude and probably more homogeneously distributed. And the turbulence amplitude does grow from all sources, but we think that this triggering of the Kelvin-Helmholtz-like dynamics is what is immediately causing these switchbacks and this flocculation. So that's all I have to say now. Remember that here's that reference again to Ruffalo et al. 2020, if you want to see this and even a little bit more evidence for this model there. So thank you very much for your attention, and we can take some, I think we have time for some questions.
Yeah, we have a lot of time for questions. Thanks, Will. Thanks a lot for very nice talk, illuminating.